What is up, everybody? It's your boy Beaumaths, aka Nuptial Failures, and I'm here today with yet another Minecraft video. That's right, back-to-back Minecraft applications. I wasn't actually planning to do this one, but I had an epiphany. I thought, hey, this would be cool to do, so we're going to be doing it. So today, we're going to learn how to make any probability you want in Minecraft. If you change your mind, I'm the first in line. Honey, I'm still free. Take a chance on me. If you need me, let me know. Gonna be around. If you got no place to go, if you're feeling down. Can't copyright a cover. So what do I mean by creating any probability you want in Minecraft? Well, for example, let's say you want something to occur with, let's say, maybe 4 in 27 chance of occurring, right? So a really specific probability, you're going to be able to do that. There's a couple caveats to what I mean by any probability. We'll see in a second that there are going to be a couple that we're not going to be able to create, at least not with the method that I'm showing you today. However, this is going to allow you to create a lot of possibilities. You'll have infinite probabilities that you can make after watching this video. All right, so to get started with, as usual, I'm going to go through some basic components here. If you're familiar with these, you can skip over this. So the redstone components we're going to be going over for the preliminaries are the subtraction mode of comparators, kind of one of the pieces of an item randomizer, but in particular how comparators interact with cauldrons, the randomization of a dropper, using all of these kind of pieces to make an item randomizer, AND gates, bigger AND gates, OR gates, and XOR gates. So if you're not familiar with any of these, I recommend watching the preliminaries, and if you are, you can skip ahead to building the actual randomizers. Comparator. Subtraction mode. So we've already talked about comparators and how they can look inside of an inventory and kind of give you an idea for how much stuff is in there. But they have another mode as well, which is called the subtract mode. So normally a comparator just looks like this, but if you right click it, that'll turn this little torch part on, and that means it's going to be in subtract mode. And what that does is it takes the pulse from behind, so whatever the signal strength going into it is, and it subtracts whatever the signal strengths going into the sides are, and then outputs that signal strength out here. So to demonstrate this most clearly, I'm going to enable a resource pack really quick here, and that's going to actually show what the actual signal strengths are on these redstone lines. ASMR transition. All right. So as we can see, here's the source, so it's at 15, but then it decreases by 1, so it goes down to 14. And then it hits the comparator, and because there's nothing going into the sides of the comparator, it's not going to be able to subtract anything from the 14, so it just outputs a signal strength of 14, and it can continue on its way. But let's say over here, I subtract another signal strength of 14, so 14 minus 14 is 0, and suddenly, hey, there's no signal strength going out, right? All right, so what if I move this back a little bit? So now there's a signal strength of 12 going in, and I pop this out, and now 12 minus 14 is negative 2, technically, right? However, it still outputs a signal strength of 0 because, well, you can't have a negative signal strength in Minecraft. So that's how that would work, and another situation, maybe I put this really close. So now this, right, because this is immediately the power source, it's putting in a signal strength of 15. So the 15 minus the 14 coming in gives you that signal strength of 1, right? And we could make this kind of go out even further. So now it's going to be 15 minus 10. We get a signal strength of 5. We could also have signal strengths coming in from the other side. So this is going to be signal strength of 12. So notice it's not just 15 minus 10 minus 12. It just subtracts the larger of these two, right? So it's not going to be subtracting the 10 off. It's just subtracting the 12 off. So 15 minus 12 gives us the 3. So it kind of just chooses one of the sides to compare with the input from the back. All right, so that's how the compare mode works for comparators. Randomizer components. So this next piece here is just showing some of the pieces we're going to be using for the randomizer. So in particular, it shows another feature of the redstone comparator. Another feature is that it can compare how full a cauldron is. All right, so if we take a cauldron has 3 states. So it has state 1 of being full with water, state 2, and state 3, right? So there's 3 different states, and the comparator will output a signal strength based on that. So we see here that the signal stops after 3, but if I take one bottle of water out, it goes down to 2, and if I take another bottle of water out, so now we just have one bottle of water in there, it goes down to 1, and then lastly it's at 0 when the cauldron is completely empty. So what we're going to be doing for this is we're going to always have our cauldrons at a height of 2. So it's got 2 bottles of water in here. And that means this comparator is going to be outputting a signal strength of 2 right there. So that means that whatever the input from this comparator is, we're going to be subtracting 2 off of it. All right. So inside of this item hopper, we've got nothing so far. But if I just put a single item in there, the strength of this comparator is going to be just 1, a single signal strength of 1. If I remove this comparator, we see that it's outputting a slight signal strength, but it's only a strength of 1. But as soon as I put this comparator back in, it turns it off because the 1 minus 2, that goes below 0, so that turns the signal off here. So what that means is that for any regular item, and these are what are called stackable items, so they're items that you can kind of have multiple of in a single slot. For any of those, that always outputs a signal strength of 1 when there's a single 1 inside of here. However, for non-stackable items, so that would be something like a sword. Notice I'm trying, but I can't actually have multiple swords in the same slot, so it's a non-stackable item. If we put that in the item hopper, that outputs a signal strength of 3. So now we're doing 3 minus 2, so we actually still get a signal strength out here, right, of a signal strength of 1. So that means that we kind of have a way of using this system here of differentiating between stackable items and non-stackable items. And that's going to be the key component of the randomizer you're going to find pretty quick here.
Dropper randomization.
The next kind of big component of the randomizer is actually getting randomization. So how does that occur? Well, droppers, they allow you to randomize things in the game. The reason is they have 9 slots. So you can put whatever you want in these slots, right? And then if you flick this, okay, it popped out a brown. And if I do another one, oh, it popped out a white. And I do another one, orange, right? So there's no rhyme or reason to it. So this is basically the randomizer in the game. Whatever you have in these slots, there's just the same chance that any of these slots are going to get shot out by the dropper whenever you give it a pulse.
The randomizer.
All right, so now that we understand all of these components, we can actually understand how the randomizer works. And it's actually pretty compact. So the way this is going to work is that inside of here, a netherite sword, and we have a redstone dust. What's going to happen is when we power it, it's going to shoot one of those items into this hopper here. And once it goes into the hopper, this comparator is going to read the signal, right? So if it shoots out the redstone dust, that's going to have a signal strength of 1 going into the back here, but that's not going to be enough to overpower the signal strength of 2 coming in from this cauldron here, right? And since we're on subtract mode, it's not going to output a signal, so it's not going to power this note block here. However, if it outputs the netherite sword into the hopper, well, what's going to happen is that is going to have a signal strength of 3 going into the back of this comparator, which the 3 minus the 2 going into the side will output a signal strength of 1, which will then be output into the note block here. And the hopper is facing into the dropper because as soon as it shoots the item into the hopper, it's just going to go back into the dropper. So it's like an automatic reset for us, which is pretty convenient. And since the dropper is randomized, there's basically a 50-50% chance that either the sword goes through and we get a signal, or the redstone goes through and we don't get a signal, right? Because it's a non-stackable versus a stackable item. So if I press the button, that means the sword must have gone through. I pressed it again and there was no output this time, so that must have meant that the redstone dust went into the hopper this time. So this allows us to simulate probabilities. And what's neat about this is we have a lot of options already, right? So for example, the output occurs in a 1 in 2 chance because one of the outcomes will give us the signal strength of 3 out of the 2 outcomes possible we have here. But let's say I add another item in there, right? Like the light gray concrete. Well, suddenly we don't just have 1 in 2 possibilities, we now have 1 in 3 possibilities. So now the chance we get an outcome is going to be a 1 in 3 chance. So there we've built a 1 in 3 probability. And one thing to be careful of is I can't just add redstone dust in here over and over again, because what's going to happen is, let me just fire this a few times. So Since the redstone dust is stackable, every time we shoot it out into the hopper, it's just going to put it back in and of itself. So each time we do it, it's going to actually be decreasing the amount of odds that we have here because the dropper only chooses the item slot to shoot out, not like an individual item. So what we need to do to ensure that this stacking problem doesn't happen is we just need to make sure that all of the stackable items we have in here are different than each other. So if I want a 1 in 4 chance of occurring, I have to add a different item. So let's maybe use the lever. 1 in 5 chance, let's add the button, right? What if I wanted like a 2 in 5 chance? So I still need the 5 outcomes, but I just replace one of these stackable items with one of the non-stackable items because now there are 2 outcomes out of these 5 that would produce a signal strength of 3 when it goes into this hopper and is read by this comparator, which would then, subtracting the 2, would give us an output. So with this, basically because we have 9 slots here, we can do any probability out of 9, right? If I wanted something like 5 out of 9, well, I just take 5 netherite swords, right? 1, 2, 3, 4, 5, and then I make sure the other slots are filled because we want 9 outcomes in total, and boom, there's your probability 5 out of 9. If I want the probability 7 out of 8, well, I remove one of these and I make sure that I have 7 netherite swords here, right? 7 non-stackable items, and then 1 stackable item for a total of 8 outcomes, 7 of which will actually give me the signal strength, right? So we see already that with a single dropper and this pretty simple setup, we have a lot of options for making probabilities. Now, what if we wanted to do something like making a probability of 1 out of 10? We don't have 10 options inside of this dropper, so how do we deal with that? This is where we're going to start using compound probabilities, which were ideas that we talked about in the previous videos where you could combine probabilities either through addition or multiplication if you had the chance of one thing and another thing occurring or the chance of one thing or another thing occurring. We're going to be making use of these by basically combining several of these probability machines by using what are called logic gates. So before we get into those probability machines, let's go over what these logic gates do because they're going to be used in some of these different components.
AND gates.
All right, so the first gate we have is what's called an AND gate. So an AND gate, essentially the way it works is that we have 2 different lines coming into the gate. So this right here is the gate. And in order for the gate to actually activate, to allow a signal to pass through, both of the lines need to be active, right? This and this need to be active. That's why it's called an AND gate. So if I turn this on, notice the note block doesn't play. And if I have this one active, once again, the note block doesn't play. It's only if they're both active will the note block actually make a sound. So the way this works is that we have 2 redstone torches here, and they're connecting to a piece of redstone. So essentially the redstone is going to be powered because it's right next to the torches, and as long as these torches are both on, the redstone will be powered. And the redstone, that's powering the block below it. And if you recall from redstone torches, if a redstone torch is powered, it will be off. So essentially, because these torches are powering this, that has this torch turned off here. So when I put a signal into this gate here, that's turning off this torch. However, since this torch is still on, this redstone is still powered, which means that this torch is also still going to be off. It's only if both are turned on that both of these torches are turned off, which means this dust will be turned off, which means this will be able to reactivate and allow a signal to perpetuate forward, which is what activates that note block. So that's how an AND gate works. And we can have multiple AND gates together using kind of a similar sort of style, where we have this redstone line that's been powered by all of these torches here, and that redstone line is turning off this redstone torch. And we can have any combination of these, but if at least one of these torches is on, the line here is still powered, which means that we're not going to be able to turn this torch on because this line is still powered. So the only way for the torch to power on and to turn the note block on is for us to have all 3 of these activated. So this, and this, and this. And there we go. So this would be a triple AND gate. And we can extend this to be as much as we want, right? You just have a ton of different signals kind of all turning off the same torch. And only when all those signals actually get deactivated, so that would be through all of the input lines, then you actually get the torch turning on. And so that would be ANDing all of those different signals. All right, so that's how AND gates work. The next thing we have is an OR gate.
OR gates.
So the way OR gates work is, well, we want one or the other signal to actually produce the output. So if I turn this on, we see it's pretty simple, right? Just a redstone line going right into the note block, so we would expect that to work. And if I turn this one on, exact same thing. And if both are turned on, well, that's also fine, right? Because what an OR is in mathematics is either one or the other or both are fine. So as long as one of those conditions are satisfied, this turns it on. So OR gates are actually pretty simple.
XOR gates.
Now, what you might wonder is how can I make it so that only one or the other occurs, right? Not both. So if both are on, we wouldn't want this line to be on, only if one is on. And that's where the exclusive OR gate comes in. So the exclusive OR gate actually makes use of the comparator subtraction. And so the way this works is that if I turn one of these on, well, what's going to happen? What's going to happen is that this has a strength of 15, this has a strength of 15, so the 15 minus 15 becomes 0 here. So this isn't actually outputting anything, and you can see that by these two torches being off here. However, over here we have a signal strength of 14. And since on the side we have a signal strength of 0, and over here we have a signal strength of 0, we're just doing 14 minus 0, so we're going to be able to continue through with our signal strength of 14 here, and that will power this redstone block. Similarly on this side, exact same logic, right? So this is 15, 15, so 15 minus 15 is 0. This isn't on, but over here we have a strength of 14, so 14 minus the 0, or minus the 0, right? 0 on either side, so 14 just goes right through and powers the block. Now, what if both are on? Notice that when both are on, it's off, and that's what we wanted with this gate, right? The exclusive OR. Only OR is allowed. We can't have both. So the way this works is, well, this has a strength of 15, this has a strength of 15, so this is 0, right? But this also has a strength of 15, right? Because even though it has 14 coming from here, the power source from here is overriding that and making this a 15, right? Because this is directly next to a power source. So this is 15, so 15 minus 15 is also 0. So both of these are going to be 0. That means neither of them are going to be active, which means we can't get a signal going through. So that is how an exclusive OR gate works. So now that we have all of this in mind, we can go ahead and actually look at making more complex probabilities. So let's start with making a 1 in 10. So we noted that we could do any probability out of 9 with this simple randomizer. However, we want to start doing more complex ones like 1 in 10. And one way we can do this is by considering, well, 1 in 10, we can split that up into 1/2 times 1/5, right? So essentially we're just looking at the 10, right, and splitting that up into two factors. And the reason we're splitting up into these two factors is because, well, we can make a half with the randomizers and we can make a fifth with the randomizers, right? So as long as we can split 10 up into basically two factors that are within the 9 that the dropper is capable of, we should be able to model the probabilities. So 1 in 10 is a half times a fifth. And how did we multiply two probabilities? Well, that was this occurring and this occurring, right? That's the chance of this occurring and this occurring. So essentially we need to take a randomizer that has a half chance, a randomizer that has a fifth chance, and then use an AND gate on them, right? And essentially the output will only occur if this half chance occurs and this 1/5 chance occurs. So that's exactly what we have here. So over here we have a randomizer, and inside there's a half chance of occurring, right? One of these two items will give us the output we're looking for, and that goes into this AND gate right here. And then over here, there's a 1 in 5 chance that it occurs, right? 1 in 5 chance. Exact same setup here, and that goes into the AND gate. So it's only when both of these actually activate, when this has the sword go in and when this has the sword go in, that this AND gate will activate, which will cause this final note block to trigger. So let's see it in action. So in that case, the 1/2 activated, but the 1/5 didn't. Same again. Neither activated that time. There we go. So that time we actually got both of them going. So I activated the AND gate and we got the final note. So that is our 1 in 10 probability right there. So then you can imagine just taking the signal and doing whatever you want with it. So if you want something to occur with a 1 in 10 chance, you just hook this up to that. All right, so the nice thing about this is that as long as we can basically factor the number, right, the denominator, because that's how many outcomes we're looking for, as long as we can factor that to have factors that are between 1 and 9, then we will be able to kind of do this setup here, right? Because we can just multiply those factors using AND gates, right? So for example, if I wanted like maybe a 1 in 12 chance of occurring, well, 12 can be split up into 4 and 3, right? I know how to make a 1 in 4 chance of occurring, and I know how to make a 1 in 3 chance of occurring, and then I just use an AND gate on those two signals. If I want it maybe a little more complicated, like something like, let's say, a 2 in 15 chance. So I know I can make a 1 in 3, and I know I can make a 1 in 5, right? 3 times 5 is 15. But I need the 2, but that's all right, because we can also do a 2 in 5. Just make sure that out of those 5 outcomes, 2 of them are going to be the netherite sword, right? 2 of them are going to be the item that will actually cause the comparators to output a signal that will then go into this AND gate later on. What if we did 5 and 12? Well, we know that a half times 5 and 6 is going to be 5 and 12, right? Multiply the numerators, we get 5. Multiply the denominators, we get 12. So here we have a 5 and 6 chance. Here we have a 1 and 2 chance. And it's the exact same setup as over there, right? So this machine right here represents a 5 and 12 probability. Now, what if I asked you, what's 27 out of 100? Okay, so you'll notice right away this machine's slightly more complicated. And what's the reason for that? Well, 100, we can kind of consider different factors. 100 is the same thing as 10 times 10, for example, or it's the same thing as 20 times 5, right? But the problem is with these is that whatever we do for these two different factors, the 10 is too big, right? We can only use factors 1 through 9 because that's all the dropper enables us to. Same thing with the 20, it's too big. So what we have to do is we actually have to split the 100 up into even smaller factors. So one way we can do that is 2 times 2 times 5 times 5. And sometimes you're going to have to play around a bit with getting the right combination of factors. But if you've watched kind of the second unit where we do a ton of different things with factors and prime factorizations, you should be relatively comfortable with that process. If not, I'll leave a link to it as a prerequisite in the video. But we have 100, that's the same thing as 2 times 2 times 5 times 5, right? 2 times 2 is 4, times 5 is 20, times 5 is 100. But this would mean that we're going to have to do 4 randomizers together. We can do a little bit better than this because we know 2 times 2 is 4, right? So we can use the 4 instead because that also is between 1 and 9. So now we just have to add 3 different randomizers together. So here we have a 4 times 5 in the denominator. That gives us the 100. And then for the numerator, we want 27, right? And that can be accomplished by doing 3 times 3 times 3. So here we'll have a 3 and 4 chance, here we'll have a 3 and 5 chance, and here we'll have also a 3 and 5 chance. So here we just take these 3 different item randomizers, right? And then we put them all together in an AND gate, right? So they all kind of attach to one of these torches, which then are powering this line, but that line is deactivating this torch. So it's only if all 3 of these torches are deactivated, namely only if all 3 of these randomizers are activated, so this and this and this, so you're using an AND gate to multiply the probabilities, only if that happens do we actually get this torch turning on, which will then be the signal that has that 27 over 100 chance of occurring. So 2 activated, but that third one didn't, so we weren't able to get that last one. Same thing there, 2 activated, but the third one didn't, so the AND gate still doesn't get activated. And we could do this a bunch. Oh, there you go. All right. So some of you may have seen a little apology post that I made regarding this video. So this video is actually my second crack at it. I've made a video before, but I actually made a pretty big mistake in there. So I've removed the video because, of course, I don't want to spread any misinformation or teach you things that aren't true. And now I'm going to tell you the mistake I made because, you know, it's still a good learning opportunity.
Romance, he made a mistake. Is he a fraud or a fake? What can he do to fix this screw up? He'll just have to tell you the truth. Romance, romance, why did you mess up the video?
right, so there are some limitations to this method. And one limitation, for example, is how could we make 11 out of 12? We know that 3 times 4 is 12, right? So we're good in the denominator. We can just take something out of 3, take something out of 4. The denominator will multiply to 12. However, to get the numerator of 11, the only way we can make 11 is by doing 11 times 1. And this is problematic because we can never get 11 outcomes. So to make a probability of 11 out of 12, we aren't able to do this with just standard multiplication. And so I thought, okay, well, we have another way of combining probabilities, and that is with ORing, right? If we take one probability or another probability, we can just add them. So I thought, okay, great. I'll do 8 over 12 plus 3 over 12. Because if I do 8 over 12 or 3 over 12, and I add them up, that gives me 11 out of 12. The problem with this is that these two events need to be mutually exclusive, right? In order to add up two events, they need to be mutually exclusive. Now, I did note that for the video. And I thought, okay, well, the problem is that these aren't mutually exclusive because when I press this button, both this could have a netherite sword going out and this could also have a netherite sword going out. So that meant they wouldn't be mutually exclusive, right? Because this and this could trigger at the same time, which is not exclusively one or the other, which means we couldn't just add them. So to deal with this, I added a reset line, which essentially if they both triggered, right? So if this occurred and this occurred, it would trigger this AND gate here, which would then cause this to go back and it would reset the trials. So basically, if this and this occurred, this would say, no, you can't have that as a trial, and it would reset it, right? So by resetting it, it would essentially mean that we weren't ever able to have an outcome where both of these randomizers triggered at the same time. And then furthermore over here, to make sure that their signals didn't actually go through to activate the note block, I had an exclusive OR gate to make sure that if both of them did trigger, this would not only reset, but the signals would get stopped here, right? Because remember, with an exclusive OR gate, we can only have one or the other signal going through here. So this was all fine and dandy, right? It seems like I had eliminated mutually exclusiveness. The problem is, and this is what I failed to account for, is that it does end up influencing the probabilities. So I claimed that this would give me 11 out of 12. The problem is that some of the possibilities we have removed. In total, there are 12 outcomes, right? The 3 times the 4, right? 3 times 4 is 12 when we make that common denominator when we add them. So there are 12 outcomes in total. So we removed the possibility where both of these can occur, but that's one of the 12 possibilities, right? So now it's not going to be out of 12 anymore, right? It's going to be out of less than 12, but that is not what we're wanting to do. We're wanting to do 11 out of 12. So that is how I screwed up, and it's not so easy to just force mutually exclusiveness on two events that aren't mutually exclusive. So once again, I apologize if you've seen the video, and in any case, I hope you've learned from my mistake. So let's talk a little bit more about what the limitations on kind of combining these probabilities are. So we can combine them, right, as long as we can multiply them through these AND gates. And just noting that we don't really have a good method to add the two, so we're going to have to stick to multiplication. And so it's going to be a situation where you do have to do a little bit of playing around, but there will be some, for example, like this 11 over 12, where you're just not going to be able to combine the probabilities that you have available in this dropper to get that number. For example, so let's say I wanted to do 63 out of 100 probability. So I know 63, that can be written as 3 times 3 times 7, right? That's its prime factorization. And for 100, that can be written as 2 times 2 times 5 times 5. Great. So at a first glance, this looks fine because all of these numbers are within that 1 to 9 range. However, the problem is that with this 100, we can make this into like 4 times 5 times 5. So we could do 3 out of 4, 3 out of 5, but we can't do 7 out of 5, right? If we only have 5 slots full, it's not possible to do 7, right? We can't get improper fractions with probabilities. And we can't do 7 out of 4 either, right? It's not going to be possible for us to have a numerator of 7 with these individual probabilities that we're combining, right? And so if we express 100's factors as factors between 1 and 9 like we have here, those can only be either 2, right? If we split this up into 2 times 2, 4, or 5, right? It has no other factors between 1 and 9, which means we can never have 7 in the numerator of one of these fractions. But we need 7 because it's a prime factor, right? There's no other way to get 7. So this would be an example of something that we couldn't make using the multiplication method that I've shown you today. So that's one thing you have to be careful of. The other thing is that if you want to have a probability, for example, say 1 out of 11, you also can't do that because 11 is prime. It cannot be formed through multiplying numbers from 1 through 9, right? It has no factors in there. It has 1 as a factor, but that requires 11 as its other factor. So it's not possible to do that. And so that means any prime number that's greater than 9, so 11 or 13 or 17, so on and so forth, those aren't going to be able to be modeled by using this method here. And similarly, any number that has these in their prime factorizations, we also aren't going to be able to model them if they're in the denominator. For example, 1 out of 22 won't work because 22's factors are 2 and 11. There's nothing we can do to get this 11 as a number of outcomes because there aren't 11 slots in the dropper, and there's no way to multiply to 11 without using 11 itself because it's prime. So these are some limitations that we have to keep in mind, but we still have a lot of options here. So next time in Minecraft, when you want to get a pretty specific probability, try and see if you can break it down into some probabilities where you can use these droppers, you can AND them together, and then boom, you will get whatever probability you want in Minecraft. But that's going to do it for me today. I hope you found this video interesting, and once again, sorry for the mistake I made, but hopefully you understand the process a little bit better, and you still have tons of options for making probabilities in Minecraft. So without further ado, you have a good one, you stay groovy, and I'll see you in that next Bowmaths video. We'll meet again. Don't know when, but I know we'll meet again some sunny day. Subscribe.